Hello, Algebra 2 students, and welcome to Lesson 3.5 on the zeros of polynomial functions. So we've talked about zeros in the past. We focused on quadratic functions. Now we're going to look at higher degree polynomials. So it could be a polynomial of third degree, fourth degree, fifth degree. So we're going to pull ideas together that we're going to use different skills that we have learned in the past to find the zeros of these higher degree polynomials. So in this first example, this should sound familiar. What are the zeros of f of x? And you're given f of x in a factored form. So hopefully you remember how to find those zeros. So pause the video. I want you to answer this one on your own first. And then when you're done, come back, hit play, and we'll compare solutions. Okay, so remember, when we have the factored form, we just take each factor and set it equal to 0. So from that first factor of x, we know there's a solution at 0. From this factor, x minus 4 equal to 0, we know that x equal to 4 is a 0. And from the third factor, we know x equal to negative 3 is a 0. So we can plot those points on the graph. Okay, so there's negative 3, 0, and 4. And now we're asked to graph the function. So what we're going to do is either use graphing calculators or Desmos, okay, whatever you're comfortable with. Excuse me. I already entered this function in the factored form into Desmos. And here's the sketch of the graph. So remember, the nice thing about Desmos is you can click on a point, okay, and get those coordinates. So what we're interested in is where are the turning points, right? So I have a turning point here, okay, at negative 1.7 and about 12.5. And then I also have a turning point down here. So let me start with this one. So negative 1.7, and this is probably going to be way off our grid, but we can just change the scale on our grid. If I go up by 2's, let's see here, I would have, let's see, 2, 4, 6, 8, 10, 12. So a little bit above the grid here. And then for my other turning point, let's see where that one was. So that's about 2.3. Negative 20, almost negative 21. So 2.3, 2, 4, 6, 8, 10, 12, 14. It's going to be about down here. Okay, now we also know that, let's see, if we were to multiply the first terms together, we'd have x times x times x. That means f of x would start with an x cubed, right? So it's third degree. We've got a positive leading coefficient. So we know that the end behavior is where this graph is going to go down to the left and up to the right. So we can pull all this together. Let's see how I can do this. I think I'm better at going downward than upward. That usually looks better. And then I'm going to go through 0 down to this turning point and then back up. Okay, so we want it to look nice and smooth. Mine's not so smooth, but you get the idea. Okay, so that's the idea behind graphing the function for now, okay, is by plotting the zeros, think about your end behavior, use your calculator Desmos to get turning points, and then fill in the sketch. For example 2, how does a multiple 0 affect the graph of a polynomial function? Well, what do we mean by multiple 0? If I have x of x equal to, let's say, x cubed times x minus 1 to the second power, and then x plus 3. Okay, so each one of these is a factor, right? And they actually have what we call a multiplicity. X is a factor with multiplicity 3. Okay. X minus 1 is a factor. I'm putting quotes there because we're repeating it as a factor with multiplicity 2 because it's to the second power. And then x plus 3 is a factor with, I don't even know if I'd really call it a multiplicity, but if I had to, I would say multiplicity 1. So the multiplicity of the factor tells us what's going to happen at the x-axis, and what the graph will do at that x-axis. When a factor has a multiplicity of 3, well, actually, you know what? I'm going to go to Savvis. I have a neat thing to show you there. Let's check this out. Okay, so we have two factors, x minus 1, and we're going to raise that to the a power, and then x plus 2. We're focusing on this one, right? This is where x is equal to 1. So watch what happens to the graph as I change that value of a. Right now, a is equal to 1. And if you notice, the graph is going straight through that x-axis. Okay, and that's what it should be doing. Now watch what happens when I change a to 2. Okay, when the multiplicity is 2, it has a turning point at the axis. Right? Kind of looks like a parabolic curve, right? And that's no coincidence. So when we change the multiplicity to 2, we get a turning point. Now watch what happens when I change it to 3. When I change it to 3, we get, it goes through the axis, it crosses through, but it also doesn't do it straight through, excuse me, like it had when it was a 1. It went straight through, just like it is at this 0. Now it has the shape of what I would call a cubic curve. Okay, remember x, the graph of x cubed has that shape at the origin. I'm going to go up to 4. At 4, we're back to turning point. Let's see, what do you think is going to happen at 5? Back to cubic curve. And then at 6, it goes back to a turning point. So again, that degree for the factor affects how the graph will look at the x-axis. So this is pretty cool stuff. This is how we're going to build upon what we just did in example 1, and now we can actually, instead of just going straight through, if you remember in example 1, all of our factors were just to the first power. Now we can have different powers and get a more accurate sketch. So again, here's when it is to the first power, straight through. That's the only time it's straight through, is for a power of 1 or a multiplicity of 1. When it changes to 2, turning point. 3, cubic curve. 4, turning point. 5, cubic curve. And 6, back to turning point. So do you see the pattern? Let's see if we can put this together. So how does the multiple 0 affect the graph of a polynomial function? If the multiplicity of a 0 is odd, then the graph passes through. If it's 1, it goes straight through. If the multiplicity is 3 or higher, meaning 3 or 5, we're still talking about odds here. If it's 3, 5, 7, then it crosses through with a cubic shape. If the multiplicity of the factor is 0 of the 0 is even, if it's an even number, so if it's 2 or 4 or 6, then we get a turning point on the x-axis at that 0. Okay, so that's pretty cool stuff to add to our tools here of how to come up with a decent graph. So let me just go back to that one more time. I just want to show you, go back to Desmos. So again, watch, I'll change this 0 here at 4. So watch what happens. Right now it's at a power of 1, right? It's going straight through. I'm going to change that power to a 2. I get the turning point. See how it's touching and bouncing back? If I change that power to a 3, cubic shape. Okay, and I could change it for any factor. So if I change it for the x squared, if I make, or for the x, if I make that an x squared, there we go. I got a turning point. Let me see if I can. Trying to stretch it out a little bit because you see it is touching, coming back down. And if I change this one, let's see what happens if I make this a 5th. Woo, okay. So you have to be careful with how you have your graph set because now we're not getting a very good picture in the middle here, but you can see the cubic shaped curve. And now it's decreasing, so it's going in the other direction. This almost looks straight, but it's not, right? Let me reduce that power, see what happens. I'll make it a square also. Oh, I'm sorry, I'm looking at the wrong side there. Okay. But you get the idea, okay? As you change that power, and this wasn't the best one to see because now it's a lot of overlapping. But if I take out the power altogether, take that one back out. So you can see the power of 3 giving it that cubic shape. Okay. Oop. And there's 4. Okay. Let's go back to the notes. In example 3, what are all the real and complex zeros of the polynomial function shown in the graph? So this is what we're going to do. You're going to be given the graph, or you'll be given the function. You can put it into Desmos or put it into your calculator, and you'll be able to find what we call the real zero, right? X equal to 2, that's a real number. So I know that one of my solutions is x equal to 2. Now the complex zeros, do you remember complex numbers? Numbers of the form a plus bi. So we're going back to using complex numbers and putting numbers in that form of a plus bi or a minus bi, where bi is that imaginary part. Okay, remember the I, do you remember what I is equal to? Hopefully you said square root of -1, right? So that means we're going to have to do some solving. We did this in our chapter on quadratics, if you remember. So how do we get this down to a quadratic? Well, now we're going to use what we talked about most recently in the last section and do division. So here I know that 2 is a 0. I know that from the graph. So I'm going to divide by 2. Look to see if we need placeholders. Looks like we're okay there. List out the coefficients. And then start the division. Okay, bring down the 1. Multiply. Add. Multiply. Add, multiply, yay, remainder 0, right? And that's what I want. And I know that because of the fact that I knew that 2 was a 0. If you know what the 0 is and you do your division and you don't get a remainder of 0, go back and check your work because something is definitely wrong. Or that number really isn't a 0, right? Maybe it's like 2.1 or 2.2, but if it's actually 2, and you do division by 2, you should get remainder 0. So now, if you remember, we had that one problem in homework, which a lot of you did very well on, where you were asked, it was that volume problem. and you're given one dimension and you're asked to come up with linear factors for the other dimension. That's what we're going to do here, except if we look at this quadratic, because remember this is degree 2 because we started with the cube, our quotient is a quadratic. So it's x squared plus 3x plus 3. Now, is this factorable? That volume problem we were able to factor, right? But you know what? If we're expecting complex zeros, you're not going to be able to factor in most cases. So what do we do instead? Well, we can complete the square, or I think quadratic formula might be a good idea here because we have that odd middle term. But that's up to you. If you like completing the square, you can use that method. So I'm going to solve for x using quadratic formula. So remember it's negative b. Let's write it out first. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So negative b is negative 3 plus or minus the square root of b squared is 9 minus 4 times a times c, and that's all over 2a, which is just 2. So we have negative 3 plus or minus, what do I have here, 9 minus 12, so that's negative 3 all over 2. Okay, so I'm almost there. That square root of negative 3, do you remember what that becomes? If you said I root 3, that's correct. So I have x equal to negative 3 plus or minus I root 3 over 2, or we can split that into fractions. I'll show you how we would write these out. So here's our 3 solutions. Remember, there's 3 solutions because it's degree 3. We have the one real solution, which is x equal to 2. And then we have the 2 complex solutions, negative 3 over 2 plus or minus root 3 over 2. So you might see it written this way. It doesn't really matter to me if you write it as a single fraction over 2 or if you separate the 2 fractions. Either way is fine. So there's our solutions, all the numbers from the complex set. So that's the first part of section 3.5. I hope you enjoyed this lesson. There's a lot more to look forward to, and we'll look at that next time. So have a good day, and I'll see you in class.